See, I said you guys would see that again. Today I have a review. The Mustool digital multimeter model MT826. We're going to open this one up and take a look at it, and we'll even take it apart and see how well this one's put together. So opening up the box, this is the first time I've seen this one. It comes in a nice carry case. And there's our meter. We've got a transistor tester. We can plug our transistors in, NPN and PNP transistors. Got a manual here. And what else is in here? USB cable. And looks like it's a thermocouple. Cool, let's open up the manual and see what this thing does. So looking at the manual here, we've got our range switch. We have our hertz switch to switch between frequency and duty ratio. That would be for checking out PWM, for example. And we can turn on relative measurements and USB as a switch for Celsius and Fahrenheit for temperature measurements. Function switch is to a backlight and data hold. Minimum, maximum, and function is to switch among your function selectors. And then our rotary switch will select AC and DC voltages, frequency ratio, and so forth. Transistor amplification test, transistor temperature measurements. On the front, we have a milliamp in common, a 10 amp reading, and our regular input for our probes. As you can see, it's factory fresh. It's never been opened. It's still in the original bag. So we'll open up the battery cover on the back. Oh, it's got batteries in it. Oh, they have a protector in here so that the batteries don't go dead. So we'll just remove that protector. Now, even though the unit feels like it's got a case on it, it actually isn't. It is rubber. It is rubberized, but this is not a case like the other meter that I got, where you can actually remove the meter from the case. I'm referring to, of course, this one here, right? It has an actual rubberized case that you can pull off of it. This one here, this is actually part of the actual cabinet itself. It doesn't come off. Comes with some nice probes, and I will say that the probes look to be a lot nicer than the last meter that I got to evaluate, which came with these 20 amp max probes. These ones here are 10 amp rated, but as you can see, they've got the category 3 shields on them. It gives you that extra, that extra rating for 1000 volts. Also, what I've noticed is these are nice silicone. Actually, these probes feel very nice compared to the last meter that I got. The probes themselves, they don't feel anywhere near as nice. These are just standard plastic insulated probes. These ones here feel to be a much better material. These ones here are silicone. So I should point out, these probes are very long. These are about 4 feet long. To give you a relative idea of the size of the unit, I'm putting it up against my other 2 meters, against the Fluke 12 on the left, the doctor meter in the middle, and here's the new one. Now, when we first turn the unit on, it's in DC voltage measurement mode. If I want to measure a DC voltage, I'll measure the voltage off of my power supply that's currently powering up that little Sony Watchman TV. So if I put my 2 probes on here, it's showing 5.8 volts, actually 5.80 or 5.81 volts, and the power supply is, according to the power supply, is putting out 5.86. So this is taking it to an extra resolution. If we check the same voltage on the Fluke, we'll see that the Fluke is going to measure 5.82, And if I look at the doctor meter, which I have to actually set the voltage manually on because it's not an auto range meter, it's showing 5.73, but it's actually putting out 5.8. So right there, this one's more accurate. Now, of course, we're not going to show you this meter. I just put it in the shot here just to show you for size-wise, because I've already done the review on that meter. This is a review on this meter. So when I do my voltage comparisons, I'm going to compare it to my Fluke 12, only because if it's accurate, it's got to be a fluke, right? Or is it, it'll be a fluke if it's accurate. One of the two, you know what I'm getting at. We're using the Fluke 12 as the reference. So I'll measure some DC voltages and some AC voltages, and we'll do some current measurements as well. And I'll do a few other measurements. We'll play around with this temperature probe and see what we can do with that, what type of trouble we can get in. I'm just going to disconnect the little monitor because I'm going to crank the voltage up. So I'll connect up the probes for both the Fluke and the Mustool. Now you get an idea. So my digital meter on the power supply is showing 5.89, and I've got 5.892 and 5.9. I'll turn the power meter down here. We'll take it down as low as this thing pretty much can go. Measure some really low voltages. So I've turned it right down to 0. I've set the output power to 0.09 volts. 0.097. Both of them are reading exactly the same. Let's turn the power up a bit. 1.39. Both are measuring exactly the same. Set for 2.39, I've got 2.402, 2.402. Exactly the same. $15.67 is what the meter says. My power supply says two meters are tracking pretty darn close. $27.6 is what the power supply indicator says. And I'll turn it up all the way. 31.78. So our power is very close. Let's check AC voltages now. So to test AC voltages, I need to put both meters in AC mode. So I do that with the Fluke. I hit the function button here to switch to AC voltage. I'm going to power this up from my Variac. Start out with the power turned down to 0. I'm just plugging some stuff in here. I've got my test cord here plugged into my 100 watt light bulb for safety, but I am plugged into my Variac and to my isolation transformer. Okay, let's turn on the power. Oh, wait a minute here. There we go. So I got about 13.5 volts. Both meters are showing about the same. As I crank up the Variac, 37.6 0.4 volts on, they're both measuring pretty darn close to each other. If I crank it up some more, now at 82.8. Turn it up all the way. And you can see that my variac that I've got will give me 151 volts. And that's normal because my variac is plugged into the 130 volt output from my isolation transformer. So with the variac you can actually increase your power a bit. If I was plugged straight into 110 volts, it would give me about 130, I think. But I can go a little higher. And that's just the way my setup is for being able to test. But here's our AC voltage, as you can see, along with the fluke. It's measuring very accurately. A little more accurately, I think, than that other one. The other one did a good job too, but the fact that it wasn't an auto range meter, myself, I'm quite kind of partial to auto range meters. So this meter here could very easily become my new favorite meter, just because it's got a nice big display on it and it does a lot of stuff. It's got a min-max range, and what that means is that say you're monitoring something and you want to see whether the voltage changed. You can hit the min-max setting, and now if the voltage were to change on something under test, like say a regulator were to fail or something, and I can do the same on here, right? I can hit min-max range, and then if the voltage drops, I can now read what the minimum and the maximum was. Now I can go here and I can press min-max. It'll tell me it went down to 58 volts, and the difference between the two of them was 24 volts, so there was a 24 volt change. On this one here, the same thing. If I hit min-max, it'll tell me that the max went to 83, the min went to 58, and then back to the current voltage. Went to, so this one here, if the voltage were to spike, it now is stored what the maximum was. It's telling me the minimum was 58, and the difference between the two was 61 volts. And if it were to go all the way up, I just cranked it to 150. I'm just turning it down. Now, as you can see, I'm down at 28 volts. It would tell me my maximum went to 150, my minimum was 28, and the difference between those two, 121 volts. That'll work with both AC and DC voltages. So that looks good. Next we'll measure resistors. So we'll check it on my fluke first. In resistance mode. This is a 220K resistor. It's red, red, black, orange, brown. We'll see what the fluke measures this at. Looks like the fluke is measuring it at 224K. So let's go over to this one. We'll set this for resistance. $223.7. So resistance wise, we're right there. Accuracy wise, it's great. This one's a 1 ohm resistor. Now you got to remember, when you're measuring low ohms, you got to take into consideration what is the resistance of the leads. If I short the leads together, 0.0 ohms. That's pretty good. What's this one going to measure when I measure this 1 ohm resistor? It'd help if I can actually, I'll take these. I'm going to take the class 3 probes covers off here. It just makes it a little easier to work with them. 1 ohm, exactly. Dead on. 1 ohm exactly. How does the fluke handle this. Now remember, my probes are measuring 0.4 ohms, 0.3 ohms, so I would expect this to measure about 1.3 because there's some internal resistance on these probes, and it's measuring 1.4. 0.4 for the probe, so it's accurate too, dead accurate. What else can we measure on this thing? We press the function, it should go into, I think it's capacitor, that's ohms, diode test, and nanofarads. Ohms, continuity, diode test. This should measure capacitance. If I push this one into capacitor test, I have here a 3300 microfarad 10 volt capacitor. So we'll hook this up on the fluke and see whether it says it's 3300 microfarads. It's going to take a minute to charge up, and it's actually coming in at around 4000 microfarads, which is pretty normal for an electrolytic. We'll discharge the capacitor here. We'll do the same test and see whether this one will measure a capacitor of this value. Connect the probes. 3931. This time I have a 47 microfarad capacitor. Okay. So 48.41. You know, as it says UF. This one here on the fluke. .6. And once again, when I had that big one, see, it's not going to microfarads, it's going to M farad. So this is like 1,000. So 3,934 microfarads, because you got to move the decimal point over 3 to get microfarads, and this is a 3,300. So that's measuring that exactly. Let's measure some real small ones. Here I have a 0.1 microfarad, 0.109, 0.11. And this is 101 nanofarads. Remember, you have to move the decimal point to get microfarads. You would move it over 3. Because it's measuring, you have to look at the display, it's measuring in nanofarads. So in microfarads, that's 0.1 because you move your decimal point over 3. So 0.1 microfarads. So it's accurate for low value capacitors, and it's accurate for high value capacitors as well. For diode test, again, this is our standard function here. This is for diode test, ohms, and capacitance and continuity. So we press the function test to get to diode test. We can test our transistors and diodes this way. There's our voltage drop, 0.592 on this diode in one direction. The other direction will be open. This is a new diode, obviously. So our voltage drop 0.593. We'll take a look at how the fluke does it. So pretty close, 574. This one was 5.9. 0.6 volts is typically your drop across the silicon diode. Let's find a transistor and we'll check that out too. Now I can say one thing I like about the fluke is it's got the beep. When you've got a good diode, it will just beep once, which is always nice. It gives you that go, no go, because if it's shorted, it constantly, so if you're, you know, that's one thing I like about the fluke. This one doesn't do that. This one, when it's in, this one's got a continuity mode for testing continuity. If I switch it to continuity, that's that indicator there, then it'll beep when you've got continuity. But in diode test mode, it doesn't beep. So you actually have to look at it. But I can live with that. Let's check a transistor out. This is just a big old PNP transistor, a 2N268. So our base is going to be our negative. So if I put the Positive on the collector. There's our base. Oh, this is a germanium transistor. See that? Germanium. So I got a 0.1 drop. This is an old one. I just found this. Same goes for the 0.1 drop, because this is an old germanium transistor. You don't see too many of these things around. I was just given a box. One of my neighbors came by a couple weeks ago and he just said, hey, I've got some old electronic parts in my garage I was getting rid of. You want them? And I wanted it more for the storage containers, because it gave me like 4 nice storage boxes full of old parts. And well, I got some now vintage transistors. So that's how you measure a transistor on this thing. Had that been a silicon transistor, it would have been like your standard 0.6 volt drop. See if I can find a silicon transistor. So I've got a silicon transistor here. Emitter base collector. I think this one also might be a PNP. I didn't look at the number when I pulled it. This is also going to be a PNP transistor. .7 and 0.7. The reason I grabbed one of these small ones, I just pulled it out of an old piece of electronics, is I want to measure the gain on this thing. So to measure the gain, we just have to plug the transistor into the test socket here. We have to pay attention to the basing. So this is emitter base collector. So we're going to turn it around this way so that emitter goes into here, and the base in the middle, and the collector. So we plug the transistor in to the test socket. Okay, once I've set, I have to remove the probes, it says, but I've set the transistor in here. When I plug this in, common to the milliamp, into the 10 amp position, it should give me the gain of this transistor. Oh, there it was. It just wasn't making a connection. There's the gain. 110 is the rating of this transistor. As far as current measurement goes, we can measure current on the meter as well, in AC and DC amps. I'm going to measure some current here. So we'll do some milliamp tests first. I'm going to use my power supply. I'm going to create a load, and we can actually compare it to what the reading is on the power supply, and then we'll do some amp measurements using my light bulb tester. So I'm going to pass 6 volts through a 4.7 ohm resistor. I've got my current limited down to 0.075, and of course I'm over my limit there because I'm in microamp range. We'll go to milliamp range, and I'm drawing 66 milliamps across this resistor right now. I've now set the current to 470 milliamps, and I'm now drawing 463 milliamps across this resistor, and I just dropped one of my probes. Let's take a look inside the meter and see how well this one's put together, because I think I popped a fuse. I had my power supply turned a little bit too high when I was measuring current. It's a 600 milliamp fuse, and I had it set for 600 milliamps, and I drew a little bit too close and popped the fuse. So let's pop the back off here and take a look in the back, and here are the fuses in the back of this unit. We'll check out the construction of this thing while I've got it apart. So I'll put a new fuse in here. Close enough, it's a 0.5 amp. The original was a 600 milliamp, and I don't have one, but a 500 milliamp will be more than adequate. Let's take a look at the construction of this meter while I've got it apart. So it looks to be a custom processor they've got on here. It's got a couple crystals. I think I would like to see these fastened down to the board, just because you drop something like this and the crystals could break. So I think that if these were fastened down with a little bit of silicone or a little bit of hot glue, it might be a little bit better, but can't really fault them on that because you're not supposed to be throwing your meter down anyway, right? This is kind of interesting because if you look on the board here, it's using a USB optocoupler. You've got an infrared LED here, and you've got an infrared photodiode over here. So when the unit is together, obviously this is the USB interface that goes to your computer, right? So what we have on this, I didn't expect to see this. I really didn't until I opened it up. But what we've got is we've got optical isolation. And not just using an optocoupler. We have full isolation of the meter, which is excellent because I didn't expect to see this type of physical isolation. I expected that there was going to be some type of an optocoupler on the board that interfaced to the USB, but until I opened this thing up, I didn't know what it was going to have. But here we have full isolation, complete isolation on separate circuit boards. That's outstanding. That way the meter communicates to the USB output. The computer is powering this up over USB, the interface, and this is just relaying the data from the meter to the USB port. And it doesn't get any better than that as far as isolation goes. There's no chance, because of course your computer is going to be at ground potential. Your USB bus will have a ground potential on it. So you want to make sure that there's absolutely no way that anything that's under test, any high voltage that's under test, can ever make it back to your computer. And this is physically isolating them through an optical channel by basically just using this emitter and the receiver here, which is excellent. I didn't expect to see that type of quality in a meter like this, but that's about as good as it can get as far as isolation goes. Okay, this spring here, this is to ground the board, and it actually grounds up against, you can see here, there's a plastic cover over here, but there's a metal earth around here. This is to shield the board and to provide an RF shield around the circuitry here, so that any signals that are radiating out from the areas of the board under test where your probes are is going to be shielded, so it's not going to get around, it's not going to leak out and cause any radiation problems, right, as far as electromagnetic interference. And it's also to keep other signals that might be in the vicinity, such as if you're working around a radio transmitter, for example. This ground spring here is going to create a shield around the measurement circuitry for all of your measurements that you're making. So this actually is, I'm quite impressed. Just looking at this, I'm quite impressed. The only thing I would do different is I would put some hot glue or something on the crystals, just so that they aren't floating around. My only concern is if you were to drop the meter, right, these could smack up against the board and damage the crystals inside. So I would put a drop of glue on there, but that's just me, right? Other than that, this thing looks to be, quite well built. And you've got some over voltage protection here. Yeah, it looks to be well constructed. I think I'll address that problem right now. Meter goes back together very easily. So if you ever have to open it up to change the fuses, you just pop the screws out of the back, the 4 screws out of the back here, and the fuses are easily accessible. We're going to measure some more current again. I'm going to measure the power requirements for my little Watchman TV, and then I'm going to measure some AC currents. I know the little Watchman TV only takes about 300 milliamps, so I don't have to worry about popping my half-amp fuse. So there you go, my little Sony black and white Watchman TV that I've got my logo displaying on. It's drawing 351.2 milliamps, and according to my power supply, it is saying 352 milliamps, which is what it is drawing in the amp reading. So it's exactly as it's supposed to be. We can certainly measure higher currents here. Let me load this thing down in the 10 amp range, and we'll see what type of currents we can draw through this thing. I'm going to run through a 1.8 ohm resistor now, and I'm going to crank up the current. And I'm now drawing 2.5 amps through this 1.8 ohm resistor. We'll load the power supply down some more. Okay, at 13 volts, I'm now drawing 5.2 amps. My power supply is maxing out here at 5.258, and this is measuring 5.25. And this resistor is getting nicely warm. So we'll turn that off before I burn it out, because I can't touch this resistor now. It's so hot. It's ouch. That's getting pretty warm. So our current measurement is accurate for DC. Let's check out our AC current. Now what I've done here is I've just put my AC cord through my probes, because this is going through my series light bulb. I'll switch this to AC current, and when I plug in that power cord to energize that, I'm going to basically put a 100-watt light bulb across it, and we're drawing 813 milliamps. Remember that if we do Ohm's law, I'm putting 120 volts into a 100-watt light bulb. So 800 milliamps is what we should be drawing, which is exactly what we are drawing. The temperature probe. Plug the temperature probe in. Select temperature. And it's telling me it's 18 degrees Celsius is what this is telling me it is. If I look over here at my temperature, you'll see that the temperature is 18 degrees Celsius in here right now. If I touch it, it's going to go up. If I take this and hold it to my soldering iron, Celsius, okay, Fahrenheit, there we go. Let's measure the tip of my soldering iron. Shall we do that? Will it go that high? So I'm just touching this against the tip of my soldering iron. We'll see how high this gets in terms of temperature Fahrenheit. It's up to 700 degrees now. I don't know how accurate how good the calibration on this cheap soldering iron is, right? I know I keep it cranked up all the way and it doesn't seem to be that hot. So I doubt that it's 896 degrees. I'm thinking it's probably in the 7 something. Even though it's measuring, even though my temperature readout says it's 896. Ouch! That was my finger I just touched. Well, it's at least 700 degrees. I got my finger good. I slipped. According to the specifications, it can read up to 1,000 degrees Celsius at 2% accuracy, or 1,832 degrees Fahrenheit. So this was measuring 700 odd degrees, although I was just touching the tip of the iron. This is a thermocouple, right? So I was just touching the tip of the iron. I think maybe if I were to get myself a little pool of solder and stick it into there, we might get a better reading, because I've, of course, was just making contact with the tip. So we'll try that. I'll get a little ball of solder, molten hot solder, on the bench here, and we'll dip that and see what it goes up to. It looks to be like about 700 degrees is what it looks to be. So I would say that the temperature on the soldering iron is not accurate. So that might be something worth investigating on a future video. Open this thing up and calibrate it and use the temperature measurement of the probe here. So let's look at the Mustool MT826 digital multimeter with true RMS. This looks to be dead on as far as accuracy compared to my Fluke. I think it's a great unit, and I'm going to be using it on my test bench going forward. I'm not going to test the USB functionality of it in this review because I have no software to track the meter and to do any measurements like that. But for those who have the software, I'm sure that it will track exactly as it does on the display. Thanks for watching.